So far, we have discussed energy, in an electromagnetic field and flow of this energy. We have also discussed momentum carried by an electromagnetic field, and both cases we have also discussed the conservation laws connected with the quantities above. In the case of energy, we had a Poynting vector. In the case of momentum, we had a stress tensor that was giving momentum. And now, if there is momentum, we realize there should be angular momentum too. And this is the topic of discussion in this lecture. We are going to talk about angular momentum of an electromagnetic field. So, let us begin that. Recall that for the energy, I was calculating the energy spent by charges in some volume. For the momentum, I was calculating dP mechanical over dt as integral rho e plus j cross b dV, and those gave me the definitions and conservation laws for these quantities. In particular, we had the momentum density for EM fields as epsilon 0 E cross B, or also as 1 over C square S. So, imagine this: if I take a coordinate system and there is all this momentum in the EM field, momentum density in some particular direction, then I can very easily write that the angular momentum should be equal to integral r cross the momentum density epsilon 0, which I will write outside, cross E cross B integrated over the volume, where I have angular momentum density as r cross E cross B. So, this is a straightforward definition, but like we did for energy and momentum, I would also like to get it by explicitly considering the change in mechanical momentum of charges confined in a volume. So, let us do that now. So, like earlier, suppose I have a certain volume in which there is this charge density rho r and there is this current density J. Then the angular momentum equation d by dt L mechanical on these charges will be torque on these charges. Torque is a vector, so let me write that, where the torque will be equal to integral r cross rho e is the force due to electric field plus j cross E is the force on the moving charges integrated over dV. Let us open this up, and like we did earlier, I am going to get integral r cross rho is epsilon 0 divergence of E plus r cross 1 over mu 0 curl of B cross B, and then I had minus integral r cross epsilon 0 dE dt cross B. So, all I have now is this extra r, right. So, let me just encircle this with this extra r. The other things I have worked out in the previous lecture when we were talking about the electromagnetic momentum. So, recalling all that, right. So, if you recall that, what it gave me on the right hand side. So, I have integral r cross, and all these terms together gave me some stress tensor T, where T actually had components T alpha beta, and I am taking this alpha equals 1, 2 and 3 as the 3 components for a given beta. That is what it means. In fact, it is derivative. So, let me write this as del dot. I will write this explicitly in a minute. And then I had dV minus epsilon 0 d by dt of, now there is an r cross E cross B dV, okay, where T is the stress tensor, and what it was equal to E alpha E beta minus 1/2 E square delta alpha beta plus B alpha B beta minus 1/2 B square delta alpha beta. This was T alpha beta. That is what this stress tensor was. So, let us write this explicitly. What we had was, I am calculating the torque, which is equal to integral r cross rho E plus j cross B dV, which comes out to be equal to r cross rho is epsilon 0 divergence of E dV minus integral r cross 1 over mu 0 del cross B cross B dV minus integral d by dt of r cross epsilon 0 E cross B, and then we had a minus integral r cross E cross del cross E dV. And the 3 terms which I am encircling in red gave me the stress tensor. In particular, the alpha-th component of this. So, let us write that torque alpha-th component was equal to epsilon alpha beta gamma integral r beta Then I will have the force term, which will be d by d r delta t gamma delta dV. I recall that all this force term, that is the term now which I am going to encircle in bold green on the left hand side of your screen, this, and this. They were giving me this derivative d by dr alpha of t alpha beta. So, now I am writing the terms with delta being summed over and gamma component is there. That is that term. And then I have minus d by dt of integral r cross epsilon 0 e cross b alpha term dV. And this equals the change in the mechanical momentum, angular momentum of the charges. So, I can now rewrite this as d by dt of L mechanical plus integral r cross epsilon 0 e cross b integrated over the volume is equal to epsilon alpha beta gamma r beta d by dr delta t gamma delta dV. Let us look at this equation in little more detail in the next slide. So, I have d by dt of L mechanical plus integral r cross epsilon 0 e cross b dV. Now, notice that this term is the momentum density of electromagnetic field, and this is equal to integral epsilon alpha beta gamma r beta d by d r delta t gamma delta dV, where obviously r 1, r 2, r 3 are equivalent to x, y, and z. I want to bring it to the surface term. So, I can write this right hand side as epsilon alpha beta gamma integral d by d r delta r beta t gamma delta dV minus epsilon alpha beta gamma integral delta of delta beta t gamma delta. This is the term, and this goes over to, now the first term I can write as a surface integral, right. So, but before that I will just write it like this, d by dr delta epsilon alpha beta gamma r beta t gamma delta dV minus, there is a dV here, epsilon alpha beta gamma integral, I sum over delta I get t gamma beta dV. Now, I claim that this term is equal to 0, because epsilon alpha beta gamma is antisymmetric with respect to beta and gamma exchange, and T gamma beta is symmetric with respect to beta gamma exchange, and gamma and beta are being summed over. So, this term is 0, right. So, let us stop here, pause here for a minute and ask you show explicitly that epsilon alpha beta gamma T gamma beta is equal to 0. So, what you are left with is that d by dt of L mechanical of those charges plus, now I am going to call this L of EM fields is equal to integral del over del R delta, then I have epsilon alpha beta gamma R beta T gamma delta dV, where L of EM fields is equal to integral R cross epsilon 0 E cross B dV. So, this is the angular momentum density. And the right hand side I can now write as integral epsilon alpha beta gamma R beta T gamma delta d s delta. Now, this is like the surface integral. So, it is like that force acting on the surface and its moment. So, this is nothing but integral R cross T delta component d s delta alpha component of this. So, we have now gotten the conservation of angular momentum, that is if T is 0, there is no term on the surface, you have d by dt of L total is equal to 0. That means, the sum of the mechanical momentum of a given set of charges and the electromagnetic field is going to be 0, and the interpretation we have given that L EM fields is nothing but integral R dot, usually one writes G for the momentum density dV, where G is epsilon 0 E cross B. Again, as in previous problems, best way to learn about it and see this conservation is to solve a problem. So, we are now going to solve a problem based on this. This problem is problem 15.23 of Zangwill's book, and it says the following: an infinitely long solenoid of radius b has magnetic field B equals Bz inside it. So, what you are given is that there is this solenoid of radius b and it has field B inside it. B equals Bz, sorry, Bz. So, this obviously is the z axis, this is the z direction. Inside it is a solid cylinder insulating, so that it can carry charge density of radius A is less than B. So, inside it I have a solid cylinder again of infinite length and coaxial with the solenoid. So, I have shown that it is a coaxial cylinder and is of infinite length and its radius is A. The cylinder carries charge density rho and which is uniform and surface charge density sigma will be opposite sign to rho, so that it is neutral. That means, it carries no net charge. So, the problem is 1, calculate electromagnetic angular momentum of the system per unit length. B, if magnetic field B is reduced, find instantaneous torque on the cylinder, and C, check the final angular momentum of the cylinder. Is it the same as the initial EM angular momentum? So, these are the questions that we are asking. So, let us solve this problem now. Solution. So, here is the solenoid carrying field B inside. Here is a solid cylinder carrying rho and sigma on the surface. This radius is A, the solenoid radius is B. First, sigma times 2 pi A is going to be equal to rho times pi A square, because the whole system is charge neutral. And with a negative sign. So, sigma is equal to rho A by 2 with a minus sign. The electric field inside inside the cylinder by Gauss's law is going to be equal to rho s over 2 epsilon 0 in the s direction. I am using cylindrical coordinates E s for s less than or equal to a and E outside, that is s greater than a, is 0. So, E cross B is non-zero for s less than or equal to a. So, let us calculate the angular momentum density. For that, first I need the momentum density. Which is going to be epsilon 0 E cross B, and it is understood it is all for s less than a, because outside everything is 0. So, this is going to be equal to epsilon 0 times rho s over 2 epsilon 0 in the s direction cross B, which is B in the z direction. Epsilon 0 cancels, and you get this to be equal to rho B over 2 s in the phi direction minus sign in front. And therefore, the angular momentum per unit length is going to be L equal to integral s cross rho B s over 2 the phi in front, there is a minus sign, that is the moment, and I have to integrate this. Since everything is cylindrically symmetric, I will write this as 2 pi s d s. S cross phi also comes out to be in the z direction, that is why it is a constant vector. And you work it out, then you get L per unit length to be equal to minus pi rho B a raised to 4 over 4 in the z direction. That is the electromagnetic angular momentum. So, part A is solved. Part B says as B is decreased, find the torque on the cylinder. So, why should this torque come about? It is very easy to understand physically. Here is the cylinder, it carries rho inside and sigma here. There is this initial field B, which is now decreased, and therefore, there is going to be the induced field E like this. So, it is going to push, it is going to apply a force on these charges inside, and is going to apply the opposite force, and therefore, the torque on sigma outside, and that is what we want to calculate. And all I am concerned with is E inside the cylinder up to the surface. So, I can just calculate from inside, and by applying Faraday's law. And Lenz's law, we already see the direction as I have shown it. So, E is going to be pi s square B dot divided by 2 pi s in the phi direction, which is nothing but B dot s over 2 in the phi direction. So, instantaneous torque which comes due to two contributions is going to be force on the cylinder inside. So, I will divide the cylinder into small shells of radius s. So, field is rho, or the charge is going to be rho times 2 pi s ds. Force on this will be times B dot s over 2. Distance is s, and I integrate this from 0 to a in the z direction. This is for the solid part. And on the shell, I will have minus, the force will be the other way, 0 to a. I can just write mod sigma, because I have taken the minus sign already outside. B dot a by 2 is the field times a. Times 2 pi a. There is no integration here, because this is a thin sheet. So, 2 pi a sigma gives the total charge. This is the field, and a times that gives you the torque. This is also the z direction in the opposite to the previous one, because negative charge, so minus z. And you work it out, substitute the values, and you get torque is equal to pi rho mod of B dot, because we have been taking care of the signs already, a 4 divided by 4 minus pi a cubed B dot sigma. It's in the z direction. You substitute sigma equals rho a by 2, and you get instantaneous torque to be equal to minus pi a raised to 4 mod V dot. Mod means I am just taking care of the negative sign, rho over 4 in the z direction. So, what is happening? Once again, I had this cylinder, and there is this induced field. It applies a force as shown on the solid part, and the surface applies opposite force, and net torque is then what comes out to be. Part C. As a result of this torque, what I am going to have is the total angular momentum gained by the cylinder is going to be equal to integration pi a raised to 4 B dot, only the positive part, divided by 4 rho z dt, and that is going to be minus pi a raised to 4 B rho over 4 z, and this is the same as electromagnetic angular momentum initially in the system. And as B goes to 0, this also goes to 0. So, all the angular momentum has been transferred to the mechanical momentum of the cylinder. That is the illustration of all that we worked out earlier. I will again ask you the question, as I asked in the case of momentum, is what happened to the torque produced by the stress tensor. So, I will conclude this lecture by saying that 1, we introduced the angular momentum of EM fields directly from its momentum. Then 2, when we rigorously obtained the expression for angular momentum of EM fields by considering d by dt of L mechanical of a system of charges in a volume. And 3, illustrated the concepts by solving a problem. Thank you.